I'm Peter Kennedy, the President of the Royal Irish Academy, and it's a great pleasure to welcome you all to the annual Hamilton Lecture. The lecture is organised by the Royal Irish Academy, hosted in Trinity College, with support from our sponsors IBEC and the Irish Times. So each year on this day, 16th of October, the Royal Irish Academy celebrates Hamilton Day to commemorate William Rowan Hamilton's groundbreaking discovery of quaternion algebra in 1843. The day includes an award ceremony to recognise the most gifted third-level mathematics students in their penultimate year of undergraduate studies in Ireland. Those students and their parents are in the audience today, and we're delighted to welcome them. There's also a masterclass and a Hamilton lecture given by a distinguished, internationally renowned mathematician. Our speaker tonight is Professor Maria Chudnovsky, professor at Princeton University in the US, with research interests in graph theory and combinatorics. She received her BA and MSc from Technion University in Israel and PhD from Princeton in 2003. She was Veblen Research Instructor at Princeton and at the Institute of Advanced Studies, Clay Mathematics Institute Research Fellow, and Liu Founding Professor of Industrial Engineering and Operations Research at Columbia University. She was part of a team of 4 researchers that proved the strong perfect graph theorem, for which they were awarded the prestigious Fulkerson Prize in 2009. In 2012, she received the MacArthur Foundation Fellowship. In her lecture tonight, entitled Parties, Donuts and Colouring, Some Problems in Graph Theory, she'll survey a few classical problems in graph theory and explore their relationship to the fields of research that are active today. So may I welcome to the stage Professor Maria Chudnovsky.
So thank you very much for coming. It's my pleasure to be here. Thank you for inviting me. It's my first time in Ireland, in Dublin, and I'm having a great time so far. So anyway, I hope this lecture shows how much I've enjoyed myself so far. All right, so this is called Parties, Donuts, and Coloring, and the way this lecture is structured, I'm going to describe 3 different sort of very simple problems, the kind of problems that you can explain to an interested middle school student, and then I'll explain how these problems actually started whole areas in research in graph theory and discrete math, and then I'll say something about the areas, but not much. And but the first part of the talk is actually going to be an historical section. So I gave a similar talk at NASA a couple of years ago, and at NASA they're very, very serious and very organized. And so first of all, they plan your talk for 2 different dates in case something goes wrong the first time. I think they've learned from experience. And then they ask you to send them the presentation, and so I sent them my presentation. They said, you should really talk about the history of the field. And my first reaction was, you shouldn't tell me what I should talk about. But then, after that passed, I thought, well, they're NASA. Maybe they actually know what they're doing. So I added a few slides about the history of the field, and I must say it made the talk much better. So we're gonna do the NASA version. We're gonna start with the history of the field. We're not gonna fire any rockets, but okay. So according to this most accepted story, the first graph theorist was Euler, when in 1736 he addressed the following problem. It's called the Bridges of Königsberg. So Königsberg is a city in Prussia, and in the middle of Königsberg there's the river Pregel. And the way the city is built, it's built on the 2 banks of the river, and there are 2 islands in the middle. And then there are bridges connecting the different land masses. So I drew this picture, so please pardon our appearance. But so what this is meant to be is the green stuff is land, the blue stuff is water, and the black stuff is bridges. So for example, between this bridge and this bank, we have, between this island and this bank, we have these 2 bridges. Then between these 2 islands, there's this bridge, and so on and so forth. And so the Königsberg bridge problem is, can you design a walk around the city that crosses every bridge exactly once? So you're not allowed to swim. You have to walk either on land or on bridges. And the rule is you want to traverse every bridge exactly once. So that was the question that Euler was thinking about. And he came up with an answer. Here's this again, same question, design a walk that crosses every bridge exactly once. And he came up with an answer, and that's what he came up with is, no, there's no such walk. Why is there no such walk? Because, so the walk starts and ends somewhere, but every landmass, so starts and ends in some landmass, and every other landmass you go through, you have to enter it exactly as many times as you exit it, right? You've entered, you exited, you continue. Then you enter, you exit, you continue. So what does it tell us? The only way to exit a landmass is via bridge. So what does it tell us? It means that except for start and end, every other landmass in your walk needs to touch an even number of bridges, because except for start and end, in every other landmass you enter, you exit, you enter, you exit. So then he looked at this picture and he said, well, this is not going to work here because we have 4 landmasses. So only 2 are allowed to touch an odd number of bridges, but here each of them touches an odd number of bridges. This touches 1, 2, 3. This touches 1, 2, 3. This touches 1, 2, 3, 4, 5, and this touches 3. So okay, there's no such walk. Now, probably you don't need to be Euler to figure that out, but but what he did do that was amazing is that he was able to abstract it to a mathematical problem, and in a way that nobody before him has done. So what he said is the land masses don't matter, the bridges don't matter, the water doesn't matter. What matters is that I have points and I need to go between them, and there are certain routes to go between them. So in today's language we call it a graph. A graph has, like this one, a graph has vertices, which in Euler's problem represent the 4 land masses, right? So I kept the color coding. So first of all, he noticed the water doesn't matter, so in the graph there's nothing blue. Then the green are the land masses, and the black bridges here become these black lines here that join the land masses. So this picture is a mathematical abstraction of that picture, right? And this is what we today call a graph. A graph has vertices, it's those green points. A graph has edges, these are connections between pairs of points, like those. And so he described this bridge problem as a graph problem, and then he was able to give a solution in terms of a graph. So what did he say? He said, well, I'm going to walk between vertices, so at most 2 vertices in the whole graph. So what's the question in terms of the graph? Sorry. I want to walk between vertices, and I want to traverse every edge exactly once, right? Edges are the bridges, so I want to traverse every edge exactly once. And he said it's not possible to do it in this graph because in order to do it, at most 2 vertices are allowed to touch an odd number of edges. Or today we say at most 2 vertices are allowed to have odd degree. And in this picture, 4 vertices have odd degree, so you can't do it. And okay, so that was earlier. And today we call this construction an Euler walk. So an Euler walk in a graph is a walk that starts and ends at some vertex. Starts at one vertex, ends at another, and traverses every edge exactly once. All right. So let's talk about a related problem. A related problem is called an Euler tour. So what's an Euler tour? It's the same as an Euler walk, except you arrive with a car and you parked it somewhere and you need to get back and collect it at the end. So that means not only do you want to walk between the different land masses along bridges, but you need to come back to the same place where you started. So an Euler tour means an Euler walk that starts and ends in the same place. So then let's think about it in the same way as we did with Euler walks. Now every landmass I enter, I have to exit it, right? There's no start and end anymore. Start and end at the same point. So that means every landmass needs to touch an even number of bridges, or in graph theory language, every vertex needs to have even degree. So we proved an on-leaf part of the theorem. If this is possible, if there's an Euler tour, then every landmass touches an even number of bridges. So that wasn't very hard. But there's actually a much more striking theorem. It's an if and on-leaf theorem that tells you you have an Euler walk if and only if every landmass touches an even number of bridges. You have an Euler walk in a graph if and only if every vertex has even degree. Right? So we proved that you definitely cannot do it if some vertices have odd degree, but there's actually something much harder and much more surprising that's true. If this obvious condition doesn't fail, if this obvious problem doesn't occur, then you can. And this is a nice theorem. This is a theorem I teach in my introduction to graph theory class. So it's a real theorem. OK, but I will not prove it to you. All right, moving on. So now we're done with the history by the request of NASA. Now we're moving on. So problem number 1, right? And so again, I'm going to start describing an easy problem. I'm going to chat a little bit about it a little bit, and then I'm going to tell you how it's related to what people do nowadays. So the first problem is it true or false that out of every 6 people that come to a party, either 3 know each other or 3 don't know each other? And the answer is true. And let me show you why. So here's one of those 6 people, and here are 5 others. So of those 5, either he knows 3 or he doesn't know 3, right? There are 5 here, so it can be that there are 2 he knows and 2 he doesn't know. So let's say he knows 3. Let's say he knows these 3. If among these 3, 2 know each other, let's say he and he know each other, then this is a triple where everybody knows each other. If among these 3, no 2 know each other, then this is a triple where no 2 know each other, right? Which is what we wanted. So that was case 1, right? That was the case when out of these 5, there are 3 that he knows. Now, the other case is out of these 5, there are 3 that he doesn't know. Now, notice the picture is exactly the same, and the proof is also exactly the same. So now these 3 he doesn't know. Make it a little bit less the same. So there are 3 that he doesn't know, but then same deal. If 2 of those don't know each other, then this is a triple where no 2 know each other. If every pair among these 3 knows each other, this is a triple where every 2 do know each other. All right, so this was a proof. You could probably follow it. It feels like this is the wrong way to do a proof. If you keep saying the same thing over and over again, you know that's not the right way to do a proof. So, and the reason it's not the right way to do a proof is because there's symmetry here we didn't exploit. And so we just keep making the same argument instead of saying, actually, it's all the same. So let's do it better. So we're going to model this problem as a graph. The vertices of the graph are going to be the people who came to the party, the 6 people that we're thinking about. And so every 2 people will be joined by an edge, but I'm going to color the edges. I'm going to color some edges red and some edges blue, and an edge between A and B is red if A and B know each other, an edge between A and B is blue if A and B don't know each other. So then what am I looking for? Either I'm looking for 3 people who know each other, who pairwise know each other, and that means it's a red triangle, right? Or I'm looking for 3 people who pairwise don't know each other. So that's 3 vertices, so that all edges among them are blue. That's here. That's a blue triangle. So the first thing to notice is that clearly there's symmetry between knowing and not knowing. Sounds like a very philosophical statement, but what I mean here is, there's symmetry between red and blue, right? They're just colors. So looking for a blue triangle is the same as looking for a red triangle. So then the statement we make is, if you take a graph with 6 vertices and all edges, and you color the edges red and blue, then there's a monochromatic triangle, right? That's the same as this, but said in math language. OK, so now how can you prove that? I mean, you know how you prove that. You prove that by using this, but it's much nicer now, because now we can see the symmetry. We presented this question in such a way that the symmetry is clear. So then we say look at one person. Here are the other 5. Look at the edges from him to those. Either 3 of them are red or 3 of them are blue. And I'm just looking for monochromatics, or a symmetry between red and blue. So I can assume those 3 edges are all white. Let's say red. And then I look at this triple. If any one of those is red, then this is a red triangle. If all 3 of these are blue, this is a blue triangle. Right? OK, so we proved that theorem again. And incidentally, this is best possible. If 5 people come to a party, then this statement is not necessarily true. And this is a counterexample, right? If you have a 5-person party and the outside cycle don't know each other and the inside cycle do know each other in pairs, then there's no triple, no red triangle and no blue triangle. There's no triple that knows each other and no triple that doesn't know each other. So you really need 6. And the way we say it in graph theory, we say R33 is 6. Now why do we say it like this? R is for Ramsey. There's something called Ramsey theory. And so this specific theorem is called the Ramsey theorem. And what it tells you is, so OK, let me say what R is in general. So now you want to know, is it true that in a big enough, so if I fix some 2 numbers, 1 million and 10 million, or RNS, and I want to know, is it true that in a big enough party, either 1 million people all know each other or 10 million people all don't know each other? And the Ramsey theorem tells you, yes. If it's a big enough party, huge compared to 1 million and 10 million, then the answer is yes. So specifically what it says is this. For every R and S, there exists n, so that out of every n people, either R know each other or S don't know each other. And the theorem is, right, all right, so what Ramsey theorem tells you is that RST is finite, which means there is such an n. So it's precisely this statement. So R of S and T is how many people you need at a party to guarantee that either S know each other or T don't know each other. In this example, it's R33. We wanted that either 3 know each other or 3 don't know each other. And R33 is 6. So R33 is somehow, right, it's the exact place where the miracle happens. Fewer than that, you don't have it, and that or more, you do have it. So on this slide, we prove that R33 is at most 6. We prove that if there's 6, then you have a monochromatic triangle. On this slide, we prove that it's exactly 6 because we proved that 5 doesn't work. So 6 really is the right answer. So OK, so this is, this was known a long time ago, and it's all easy. But now there are some things that are not easy even to us today. So we know R44, right? How many people do you need at a party so that either 4 know each other or 4 don't know each other? The answer is 18. How about R55? We don't know. So it's between 43 and 48. But this range was narrowed down to 5 2 years ago. I mean, it's hard to believe that with all the computers we have, this we don't know. But it's the truth. And then R66, the range is even bigger, right? It's between 102 and 165, but we don't know where it is. And so you know about the mathematician Paul Erdős. He did discrete math and number theory and all kinds of things. And the kind of most important thing, not most important, but most unusual thing about him was his lifestyle. He didn't have a home. He just traveled from place to place and did math with lots of people and sort of had tremendous influence over a lot of things that are happening to this day. But he apparently also had a good sense of humor. And so another mathematician, Joel Spencer, tells the stories that Erdős used to have opinions about this problem. And he used to say, if aliens invent the Earth and say, you're all going to die unless you calculate R55, we should collect all the mathematicians, all the physicists, all the engineers, and send them to work to calculate R55. However, if aliens invade the Earth and demand R66, then we should collect all the mathematicians, all the physicists, and all the engineers and send them to fight the aliens. So Erdős thought R66 is really hard, and I trusted it. OK, so this was that problem. And now you can generalize this, and you can generalize this. So this is already, things we don't know, right? This is already research. And there are some, more complicated things I can tell you that we don't know, but maybe it's not such a good idea. But let me tell you instead of some generalizations that I can describe to you easily. So we were asking, we took what's called the complete graph. The complete graph is the graph where every two vertices are joined by an edge. And we colored the edges in two colors. And we asked, is there a monochromatic smaller complete graph, right? We looked at K6 and wanted to know, is there a monochromatic K3? So now you don't have to demand that what you get is a monochromatic complete graph. You can ask, is there always a monochromatic, my favorite graph? Let's say my favorite graph is a cycle on 5 vertices. So for which graphs is it true that however I color the edges in two colors, I would get either a red C5 or a blue C5? That's as good a question. And and that's something you can think about, right? You don't have to think about cliques, about complete graphs. And then there's another sort of related notion that's called being Ramsey equivalent. So let's say I found a graph where however I had to color its edges, I get C5. I get C5 and I don't get C6, and I have a list of some graphs that I can always get. So two graphs are called Ramsey equivalent if what you get for every edge to coloring is the same list. Right, so I said it here more precisely. H1 and H2 are Ramsey equivalent if, and I'm sorry, I said it exactly wrong. Two graphs are Ramsey equivalent if you get them for two colorings in the same graph. So then people ask what graphs are Ramsey equivalent. And first of all, it turns out we don't know. Turns out this is an open question and people are thinking about it. It was only recently proved that the complete graph is not Ramsey equivalent to any other what's called connected graph. There's a very recent theorem about what a complete graph on 4 vertices plus an edge is Ramsey equivalent to. So somehow it's a completely unexplored and difficult field, and yet it's very close to this problem. All right. So then there's another generalization you can think of. This one is less unexplored, but in some sense more striking. So what if I don't 2-color? What if I 7-color or 10-color? Right? I give you a big complete graph, and I color the edges with 200 colors. And I want to know, is it true that there is still a relatively large monochromatic complete subgraph? And the answer is yes. If the size of the graph I started with is much, much larger than both the number of colors I used and the monochromatic thing I want to get at the end, then the answer is yes. So somehow what it tells you, right, is that even if everything looks terrible, there's a little bit of order you can hope for. And this is a very useful fact. I mean, this is useful when you think about sequences. This is useful when you sort of think about various behaviors, and there are many different kinds of behavior, but actually you can still find a relatively large subset when all pairwise behaviors are the same. I don't want to go into details, but it's a very useful theorem in very many ways. And right, I mean both in math and other ways. All right, so moving on, problem 2. If you lost interest in Ramsey theory, now is my next chance. So what's problem 2? Problem 2 is about coloring maps. So you're given a map, and you want to color. So it's a map of countries, right? It's called a political map, and you want to color the countries, but in such a way that if you look at this map from really far away, you can immediately tell where one country ends and another country starts. So what that means is that two countries share a border, and by border I mean not just a point, but an actual interval of a border. Then I want to color them in different colors. Right? That's what I mean when I say looking from far away, I can tell. All right, so then the question is, how many colors do you need? Right? I give you any map, how many colors do you need? And it turns out that the answer is 4 colors is always enough. I need to be a little cautious with that. 4 colors are always enough, provided every country is what we call connected, or what people call contiguous. So you're not allowing islands. Like when I give this talk in America, I say there's no Hawaii, and you can use your own, right? But if every country is just sort of some kind of a disk or a connected region of the plane, then 4 colors is always enough. And there's a sort of nice story to this problem. It was actually, I guess I can still show this. It was actually proposed, this conjecture was proposed by a cartographer, not by a mathematician. I guess he had more experience coloring maps than mathematicians did, and he noticed that every map he tried to color, 4 colors were enough. So he made a conjecture. He said 4 colors is enough. And he made this conjecture, I think, in 1863 or something like that, definitely mid-1800s. And it stood for many years. It stood till the mid-1970s, so more than 100 years. And the time it was solved was when computers came into play. Apple and Haken used a computer to solve it. And what they did was they first showed that, so there are 2 halves to the proof. One half is what's called reducible configuration. So they had the list of things, the list of configuration in the graph they noticed that showed you this is not the smallest known 4-colorable map. So what they showed is if I can color everything smaller, then I can use this configuration to somehow color its inside and color its outside and get a coloring of the whole map. So they had these reducible configurations. And then the second half of the proof was, well, there was a list of things that didn't admit a reducible configuration. You actually had to check them. But that was finite. That list was finite. And then they used a computer to check this finite list. So this was the first computer-assisted proof. It was 1972, right? It's only, about less than 20 years into the existence of computers. It depends how you measure, but something like that. And, it's a very elegant fact that every map can be colored with 4 colors. But I think it's a much more important thing that they came up with the first computer-assisted proof. Now it's now people do it all the time, and their arguments: is it good? Is it bad? Is it a proof? Does a computer make a mistake? Does a person make a mistake? But back then, I'm sure it was an amazing thing, right? To sort of this thing that 20 years ago could maybe do 2 + 2, and now it proves the theorem. So that was that, and so unfortunately, after they did that, people had a lot of doubts. Somehow, when you do something for the first time and it's this huge, massive thing, you make mistakes. And so it seemed that maybe they were not very careful proving that their list of, right, so they had this list of things to check. Maybe they were not very careful proving that this list is exhaustive, and so on and so forth. So then in the 1990s, there was another team, Robertson, Seymour, Sanders, and Thomas. And they did basically follow the same idea, but did it much more carefully so that people could actually believe it. So there's another proof, which is much neater, but same principle. You have a list of reducible configurations, and you have then you have a finite list of cases you need to check, and then the computer checks them. And I think the 1990s proof had about 300 configurations, 300 things to check, and the original 1972 proof had maybe 600 things to check, but same idea. All right. So, but let me tell you a little bit more about the problem and not about its history. Okay, so we say 4 colors is enough. The first question is, do you really need 4 colors? Maybe 3 colors is enough. And it's not hard to convince yourself that 3 colors is not enough, because look at this map, right? So the countries are this triangle, this triangle, this triangle, and that thing outside. And you can notice that every 2 countries share a border. Every 2 countries share an interval of a border. So there are 4 countries, you need 4 colors. Okay, so then you might say, well, this is obviously a pathological case of every 4 countries, if there are 4 countries that pairwise share borders. Maybe that's the only time you need 4 colors. Maybe in all other situations, 3 is enough. And the answer is no, because look at this thing. So here the countries are the triangles and the outside. And here we do have countries that don't share borders, namely this and that. They share a vertex, but they share like a point, but we decided we don't count that as a border. So it's not that every 2 countries share a border here, but I claim you still cannot do it with 3 colors. Why not? Well, let's try. So I can assume this huge outside thing is colored with color number 1. And then for the triangles, all that's left is 2 and 3 because they all share a border with the outside. But then let's see if we can. So I can color this 2, and then this must be a 3 because they touch, and then this must be a 2 because they touch, and this must be a 3 because they touch. But now he's in trouble. He touches a 2 from here and a 3 from there, and so there's no color for him. So really here you still need 4 colors. All right, so what about, now this was maps of the Earth, right? So it's a map that you draw either on a piece of paper or in a sphere, which is the same. What if you're more ambitious than that, and you want to think about maps on other planets, and maybe these planets are shaped more interestingly. So what about a map on a torus, or what we call a donut, or a map on a pretzel, what we call a double torus, or generally I take a surface of a certain genus and ask how can you color a map on it, and so it turns out that the answer is for every surface there is a constant, so that this number of colors is enough. Like it's 4 for the sphere or the plane, it's 7 for the torus, it's some number that I don't remember now for the pretzel. But what about calculating the smallest c? And it's not hard to prove that some number works. For example, for the Earth, proving that 6 colors is enough is easy. Proving that 5 colors is enough is pretty easy. Proving that 4 colors is enough took 120 years. But for other surfaces, actually, somehow, what you get by the easy argument is the right answer. But I don't want to talk about that. Okay, so right, so there's a question: what's the smallest number that works? And that's hard, but there's a field related to it. There's a field of graph theory that's related to it. And that's called graphs on surfaces. So what do I mean by that? Or topological graph theory. And what do I mean by that? Well, so I need to color this map. Let's represent it as a graph. Let's think of it as a graph. And then I can talk about graph theory. I can think of this graph as being drawn in the surface. And I can, and the way you would represent it as a graph, you would say, for every country, I'll have a vertex, and 2 vertices are adjacent if the 2 countries share a border. And then my question is, I need to color the vertices of the graph so that if the 2 vertices came from 2 countries that share the border, then they get different colors. Or just in terms of the graph, I want to color the vertices of the graph so that if 2 vertices are joined by an edge, then I need to color them with different colors. Except this is not just any graph. This is a graph that somehow you got from a map on a given surface by replacing each country with vertex. And then it's an interesting topic because these graphs are very non-general and they have a lot of beautiful properties, and people think about it. And again, I'm not going to go into details, but it's a field of research many people work in. All right, number 3. So number 3 is a field I work in, so I'm going to talk more about this. This is something called graph coloring. And this is related to what I just told you about map coloring, but more general. So let's start with an example. Suppose I have a bunch of cell phone towers, and they all need to transmit signals. And the problem is that some towers might interfere. Maybe they're close to each other. Maybe they tend to transmit at the same time. There are all kinds of reasons why transmissions from two different towers might interfere. But some pairs of towers interfere, and so I should not allow them to transmit on the same frequency. And then the question is, how can you assign frequencies to cell phone towers in such a way that there's no interference? All right. Okay, so let's say this with a graph. I'm going to build a graph where the vertices of the graph represent the towers. So here I have 7 towers. And then I make 2 vertices adjacent if the transmissions from the 2 towers may interfere, which means, So now what's the question? The question is assign frequencies so that adjacent vertices get different frequencies. And now call frequencies colors. And we get what we call graph coloring problem. What's a graph coloring problem? It's like map coloring, except you start with a general graph. Color the vertices in such a way that if two vertices are adjacent, then they must get different colors. So, I mean, there's an easy solution for that, right? Color every vertex with a new color. But somehow that's not the point, right? It's supposed to be an interesting problem. So, if you think about frequencies, you can think about like you need to pay money for each frequency you use, so you want to do it with as few frequencies as possible. You want to do it with as few, and mathematically you want to do it with as few colors as possible. An application that might be closer to some people's hearts and assigning frequencies to cell phone towers. So I got married several years ago, and as you know, one of the biggest challenges toward marriage is the seating chart for the reception. And so, my husband, who is not a mathematician, was very nervous about that. Also, most of the invitees were his family, so he was double nervous about that. And then I said, I think I can work some magic here. Give me this list. And so what's a seating chart? You make a graph where the vertices are the guests, and you make two people adjacent if they hate each other so much you cannot put them at the same table. And now you need to color the vertices by table numbers. And the rule is people that sit at the same table, there are no ages between them. People that sit at the same table know to hate each other. Now, okay, so at least that's a problem I understand, right? In general, it's a very hard. In general, it's a hard problem. In general, it's what's called an NP-complete problem to create a seating chart or to color a graph. But the thing is, if your guests are sort of reasonable people and everybody only hates one or two people, it's very easy. The greedy algorithm works. The greedy algorithm means just do the best you can. Put everybody at table one until you find somebody who hates somebody at table one, and put him at table two. So put everybody at the earliest table you can, and hope for the best. So that's what I did. And our family is a reasonable family, so I was able to show my powers. And we had. So then, how do you explain why you need as few tables as possible? Oh, they're centerpieces, right? Everybody understands you want to minimize the number of centerpieces. This is not math. This is clear. Okay, so anyway, so lots of applications. For a while I was going to make an app for seating charts and make a lot of money, but I never found a partner. I don't understand how I never found a partner for that. It's such a good idea, but nobody would talk to me. All right, so back to graph coloring. Here it is again. Given a graph, color the vertices with different colors. The rule is if two vertices are adjacent, then they get different colors. And the goal is to use as few colors as possible. And the smallest number of colors that you can use for a given graph is called the chromatic number of this graph, chi of this graph. Okay, so, and that's something that graph theorists study, the properties of the chi, the properties of the chromatic number of a graph. The first thing to say about it is that it's NP-complete to calculate it in general, but there are some special cases where you can. The next thing to say about it is there's an obvious lower bound on the chromatic number. So what's the lower bound? If I have a graph and I have 20 vertices all pairwise adjacent, then I need at least 20 colors, because these 20 vertices, each of them has to receive a different color. Right? If I have 20 people, no two of which can sit at the same table, I need 20 tables. There's nothing to be done. So the first, fact or theorem, somehow a fact is an easy theorem, right? So the first fact is chi is at least this parameter that's called omega. Now, why the chromatic number is denoted by chi, I understand. Why the size, the biggest number of pairwise adjacent vertices is denoted by omega, I don't understand, but it is what it is. It's called the clique number of a graph. So the first fact is that chi is at least omega. So then you can say, well, maybe that's the only obstacle. Maybe omega is what you need. If you look at a graph and you find that there's no 101 vertices pairwise adjacent, only 100 vertices pairwise adjacent, then 100 colors is enough. And turns out this is completely false. So it is not true. Chi is at least omega. It is not true that omega colors is always enough. Let's do some examples. So here's one. Well, here's one example. So what is this? This graph is called C5. It's a cycle of length 5. So you draw 5 vertices on a circle, and you make consecutive pairs adjacent and non-consecutive pairs non-adjacent. In fact, I have a picture here. So what's the clique number? What's the biggest number of pairwise adjacent vertices? Well, it's only 2, right? There are adjacent pairs. You can look at it for a minute and notice there are no pairwise adjacent triples. So omega is 2. What about the chromatic number? Well, the chromatic number is not 2, because if I wanted to color this graph with 2 colors, so what would I do? I would go 1, he must be a 2 because he's adjacent to a 1. He must be a 1 because he's adjacent to a 2. He must be a 2 because he's adjacent to a 1. But then I don't have a color for him, right? He's adjacent to a 1, so he's not a 1. He's adjacent to a 2, so he's not a 2. So I'm stuck. So the chromatic number is not 3, and in fact, it's not 2. And in fact, the chromatic number is 3. And then you can generalize this amazing observation and notice that for any odd cycle, any odd number of points I put in a circle and make consecutive ones adjacent and non-consecutive ones non-adjacent, the clique number is 2 and the chromatic number is 3. So we constructed an infinite family of counterexamples to the statement chi equals omega. All right, that's good. Well, maybe this is it. Maybe if you're not one of those cycles, then chi and omega are the same. And the answer is no. So here's another infinite family, but it's a little bit of a cheat because it's related to the first family. So these are what's called complements of cycles. What does that mean? So in general, in graph theory, to take complements means to reverse all the adjacencies. You start with a graph, and then its complement means if a pair was adjacent here, you make it non-adjacent there. If a pair was non-adjacent here, you make it adjacent there. So these graphs are meant to be complements of odd cycles. So what does that mean? Let's do an example. So this was C5. Now what's a complement? And let me now give names to the vertices, A, B, C, D, E. So now what's a complement? It's that. Still I have A, B, C, D, E, right? Same vertices. But the adjacencies are exactly the opposite. So A used to be adjacent to B and E. So now it's going to be adjacent to A and C. B used to be adjacent to A and C and non-adjacent to E and D. So now I'll make it adjacent to E and D. C was adjacent to these two, non-adjacent to those two. So I'll put this in, and you can stare at it for a minute and notice that I'm not going to get any new edges if I keep going around. So this is the complement of C5. Now another thing you notice is that it's actually still the same graph. You just go A, C, E, B, D, or as we say, isomorphic. But in general, it's a little more interesting. If you start with a C7 and you do, so C7 means this. If you start with a C7 then and take complements, you're not going to get C7. You're going to get some new graph, which is called C7 complement, and it looks like this. There's a much nicer way to draw a C7 and actually have a necklace, which is a C7. And I don't know why this necklace is not commercially available. Somebody made it for me, as a gift, and it's a lovely pattern. Again, another startup that's waiting to happen. All right, but why am I showing you these graphs? Because that's another infinite family where the clique number and the chromatic number is different. So what you get is you can take every second vertex, except it's an odd number. So if you take every second vertex, it's a little less than half. And that's the biggest clique you can get. And on the other hand, you can see that in order to color, you need a little more than half the number of vertices colors. So they're not the same. All right, so that's another infinite family. But okay, so now you probably don't believe it at all. You think, chi and omega are always different. There's nothing to be done. But actually, it turns out that sometimes they are the same. And it turns out the times that they're the same are the nice times, the good times. And there was a French mathematician, Claude Berge, who said these graphs are important. Graphs where chi and omega are the same are important. And except if you think about it a little bit more, you want to be a little more technical about it. You want to say not only chi and omega are the same in the graph, they're still the same however you delete vertices from the graph. If today is the first time I heard about graphs and vertices, this is not the time to dwell on this distinction, but if somebody here knows what I'm talking about, I don't want to say something completely false. So a graph is perfect if chi and omega are the same however you delete vertices from the graph. So for example, this graph is perfect, right? It has 4 vertices and the chromatic number is 4. This graph is not perfect. Why not? I'm sorry. This graph is perfect because it's a complete graph on 4 vertices, right? It has 4 vertices and they're all pairwise adjacent, and 4 colors is enough, and you can check that as you delete vertices. It's the same. This graph, this graph is not perfect because the clique number is 3, 1, 2, 3, right? You don't have 4 pairwise adjacent vertices, but the chromatic number is not 3. And the reason the chromatic number is not 3 here is exactly the same as the reason we couldn't color this map with 3 colors. Because if you take this map and you make a graph out of it where the regions of the vertices and 2 regions touch if they share an edge, then you get exactly that graph. But it's so beautiful. I'll say it again. So why is this graph not perfect? The clique number is 3. I claim the chromatic number is 4. Suppose the chromatic number were 3. I can assume it is colored with color 1. And then what's left on the outside, which is a node cycle of length 5, I need to be able to color with 2 colors because I can't use 3. And we already showed that's impossible. All right, so just a small illustration of the thing I told you not to think about. So perfect means perfect is not exactly the same as saying chi and omega are the same. Because, for example, in this graph, right, chi and omega are the same. Omega is 3, 1, 2, 3. Chi is also 3. You see I 3-colored it. But this graph is not perfect because if I delete that guy on top, then I'm going to get this graph. And again, we already know that here chi and omega are different. So that one is not perfect. All right, so anyway, and it turns out there are some very natural, beautiful graphs that are perfect. It also turns out that the concept of being perfect, so Claude Berge came up with this idea in 1961, and it turns out this notion generalized a lot of things that people already knew by then. So somehow there was one word to say many theorems that were already known, which, in math we always like that, right? So perfect graphs became popular. People started thinking about them, and Berge made a beautiful conjecture about them. So if I give you a perfect graph, and I want to know what can you get from it by deleting vertices. Certainly I cannot get anything with chi different from omega. So I cannot get a node cycle, and I cannot get the complement of a node cycle. But he conjectured that this is it, that a graph is perfect if and only if you cannot get from it by deleting vertices a node cycle or a node anticycle, or the complement of a node cycle. And he conjectured it in 1961. It was open for 40 years until Neil Robertson, Paul Seymour, Robin Thomas, and myself solved it in 2003 to 2006, depends how you count. As you might know, there's a big lag in math publications. So, we proved it in 2003, but it finally appeared in 2006. So anyway, so it turns out perfect graphs are actually as nice as Berge thought they were. They're precisely the graphs that don't contain the obvious abstraction for being perfect. And then there was a question, can you recognize perfect graphs efficiently? And it turns out the answer is also yes. That was done with this group, also around the same time. And so anyway, so in somehow perfect graphs are, in some sense, a culmination of graph coloring. They're the nicest graphs in terms of graph coloring, which is why they're called perfect. And let me stop here. Thank you very much.
Given the day that's in it, this being Hamilton Day, we just have a little souvenir for you. In year 2005, UNESCO World Year of Physics, Ireland, its own Hamilton year, and these special edition €10 coins were minted, and we have one of these. So, Professor Chudnovsky.
Thank you very much.